full disclosure, I gave this clinic back last July to the JRD when they had a meeting here in Lake of the Woods. But it's a follow-on to a clinic I did back at the joint JRD Potomac Minicon in November of 21, where I got into what signals are. So let's move right along here. Today we're going to pick up after that clinic. We're going to do a quick review of the basics of signaling. We're going to spend some time on aspects, indications, and a few FRA rules. Then we're going to design a chart of signal aspects and indications that you can use on your model railroad. And then we're going to design 4 different applications of those signals to your railroad. And I'm going to give you a little background on myself. So we'll start with that. I'm a model railroader since a long time back. And I've been a member of the JRD here since 2018. I was the New Jersey division before that. I'm a licensed professional engineer, and I'm a retired signal engineer. I had 38 years of experience and retired twice, once from NJT, once from Amtrak. I've worked on various different signal systems in my career, both at the railroads that I worked for and while I was working for a supplier. I also belong to several associations that gave me that ability to get the experience with all the other railroads. We used to meet regularly and discuss indications of significance in the signal business. Well, what was interesting to me was that each property seemed to be different, seemed to be unique. But early on in my career, I figured out that instead of being unique, they were very, very similar. And most of the requirements are now FRA rules and regulations that actually govern what must be done. It's no longer a you can, it's must. I was also qualified on NORAC rules and spent many years advising the committee chairman on the signal aspects. So we'll get into our quick review. What is a signal anyway? Surprisingly, the railroad rule books don't define a signal. They define specific signals, but there's no general definition of a signal. So I went to Webster's dictionary, and in their third item, a signal is something such as a sound, a gesture, or an object that conveys a notice or warning. Okay, so this works for railroad signals. We're going to talk about the railroad signals. I went over all kinds of signaling in the previous clinic. Today, we're going to focus on block signals and automatic block signals and interlocking signals. And these are the definitions right out of the NORAC rule book. And you know, here's the classic failure of the definition, because it tells you that a block signal is a signal. An automatic block signal is a signal. Interlocking signals are signals. And nowhere do they tell you what a signal is. And, you know, 38 years, I never realized that it wasn't in the rule book. But we don't need to worry about that. I'm going to give you a quick review of the history and why we need to have signals. The biggest issue is line of sight versus stopping and how far apart the signals are. Also, we need to consider opposing traffic. If you remember when we went over stopping distance, it was easily approaching a mile. And in reality, we're looking at 2 miles in today's world to get a heavy train stopped safely. We had previously discussed manual block at some length, and one of the issues there was that it requires communication with both ends of the block. The operators have to be able to communicate or some other means. Some systems did actually use track circuits through the block. We'll talk a little bit more about track circuits later. Manual block works well for light traffic densities or scheduled train operations. And the modern equivalent today is a Form D or a track warrant, something like that, where instead of going through a block operator, the authority is communicated directly to train crews. And that's probably closest to how most model railroads operate. But we're going to talk about how we can add signals that can govern the train movements and also add some animation to your layout. One of the other places that it's important to have signals is at junctions. You don't want to give conflicting routes the authority to proceed and collide. So the safety requires what we call interlockings, where and I discussed this previously, that movements must succeed each other in the proper sequence and blah, blah, blah. One of the distinguishing features of interlockings is many used to be manual. Most all were manual, where there was an operator right there that either operated a Saxby farmer lever, or they operated a machine, or even a miniature machine. And then we have remote control, which is essentially the only way it's done today, sometimes called CTC. CTC was a patented name, but way back when, it's long since expired. Then we're going to go into automatic block signaling. One of the major advantages when automatic block signaling came into effect was that we were able to get increased traffic density and efficiency through the blocks, because trains could now follow each other at stopping distance apart, instead of having to have a manual block that may be many stopping distances apart. And what made this practical was the invention of the track circuit. Again, I talked about that previously. I'm not going to go into the details of that today. But the key thing with automatic block signaling is the signals are spaced and configured to adequately warn the trains stopping distance away. So they have to be a minimum of stopping distance away. And that's what we're going to focus on what we want our model signals to look like, that they're stopping distance. And then when traffic control circuitry was added to the automatic system, it allows bidirectional traffic to move on a single track railroad. And that's when the CTC really became efficient, because the dispatcher could use the signaling system to make sure that he didn't have conflicting trains. He didn't have to have two tracks. They could run on the same track in either direction. Today, the new systems don't even require line wires or external wiring. They actually use the rails themselves to send the signal control information, as well as the detection of the trains. So now we're going to get into aspects versus indications. This is one of the hardest things I had to learn way back when. And basically, this boils down to what you see versus what it means. Most of the rule books are very similar in how they describe aspects and indications. And the way I think it's easiest to remember is that an aspect is the way a signal appears to an approaching train. So all the A's there: aspect, approaching, appearance. And that's the key thing for defining a signal. The indication interprets what the aspect is trying to tell you and provides instruction on what to do when you can see the aspect. So again, we're going to look at the eyes. Indication interprets. Indication is the instruction on what you see from the aspect, which was the appearance. So to design a signaling system, we need some basic indications. So let's go through some of them. Let's go through all of them, all the ones we're going to use on the model. Of course, we need a stop indication because there's either a hazardous condition ahead, or we need to keep, or just some reason to keep a train from proceeding, say at an interlocking where there's a conflicting route or an opposing train coming at you. We need a go ahead that tells you to look out for some sort of a restriction, such as in the prototype, a broken rail, an open switch, or following another train. On the model, we don't worry about broken rails. We need an indication that says to approach the next signal prepared to stop. So we've got the signal there that's protecting the restriction, but we need to tell the train somehow to come up upon it and be prepared to stop, because he might not be able to see it from a distance, and he might not be able to get stopped if he does see it at the last minute. Again, that's on the prototype, not the model. We want to emulate it on the model, though. We need an aspect, an indication to say approach the next signal at some reduced speed. And I'll get into more of the details of that as we develop that one. We also need one to say, okay, keep going. There's nothing ahead, nothing to worry about. Proceed at maximum authorized speed because there's no restrictions within stopping distance. So let's give these aspects these indications names, and we'll put them in a chart. So this is what a basic signal chart looks like. We have the name, we will develop the aspects, and we have the indication. So let's talk about the aspects that are going to communicate those indications. What's it going to look like to the train, or in our case, what's it going to look like along the model railroad? Now, what I'm going to develop today is mostly pre-positive train control rules, or where positive train control supplements the existing wayside signal system. There are newer positive train control systems that have modified the wayside aspects significantly and the wayside aspects give different things that I don't really want to go into today, and we don't need them on the model. If you want to model PTC on a model railroad, go right ahead, because I don't think it would really add anything. So there are FRA rules that require some very minimum things of aspects. The railroads can't just arbitrarily go out and say, I want to put a pink light up and tell the crews that means something. No, because the FRA says that they shall be shown by very specific things. And specifically, they say, well, it could be the position of a semaphore. It could be the color of lights. It could be the position of lights. It could be flashing of the lights, or any combinations of those. But they also say that the fundamental indications shall conform to the following. So I was saying the pink, well, you got to use a red one, or a series of horizontal, or a semaphore blade horizontal to indicate stop. And you've got to use a yellow light, a lunar light, or a series of lights or blades in the 45-degree quadrant to indicate that a restriction of some sort may be required. And a green light, or a series of vertical lights, or a semaphore blade in a vertical position in the upper quadrant, or 60 to 90 in the lower quadrant, shall be used to indicate proceed at authorized speed. So you can't really deviate from these. If you do, it would require an exception to the rule, and FRA doesn't give those out freely. So let's proceed with our design now. So in order to do a design, you always need to have paperwork. And so what we're going to do is come up with a drawing. So we'll start with the basics. There's a signal mast. Sort of looks like one. We're going to use the upper quadrant semaphore blade to represent the three possible aspects that could be on a particular arm of a signal. It's clear that those could be semaphore positions. They could also be position light positions, and I'll show you how we interpret them as colors as we go along. So the FRA said colors, positions, and here we go. And then we're going to just add those signal heads. I'm going to call that a head. That device there, we'll just call this a head once we attach it to the mast. And then we can do flashing, we can do marker lights, we can do numbers, we can do normal positions. And what I've shown you here now in this chart is the normal position for this aspect. So the indication of stop is shown by the darker blade position on the head there. I'm skipping the restricting for now. We'll go back to that one in a little while. And for the approach, we do a similar thing. We show the blade in the 45 position. That could also correspond to a yellow light. We show an approach medium, which says approach the next signal at some reduced speed. What we're doing here is flashing that 45-degree aspect. We can only do this with color lights or position lights. So you can't do this with a semaphore. And then we have the clear showing with the green, with the vertical position of the blade or green light. So this is just the way we draw it on a sheet of paper that can easily be copied. This is long before there were color copiers out. So let's build a simple two-block system based on what we just talked about. So here's a basic two-block signal system. We've got the train located in block A. We've got block B, which is at least stopping distance from the entrance of block B is at least stopping distance from block A. And then we have block C, which is at least stopping distance out. So here's our signal at A protecting the home block there. You can see we're showing the horizontal aspect. At the distant down at B, the entrance to B, which is stopping distance away from A, we're going to show the 45, which says, if you remember from the chart, approach the next signal prepared to stop. So there's the sequence. In a two-block system, there's the sequence. And the next signal says, well, as far out as I can see, as far out as I can see, there's no hazard, because here it's stopping distance and here's the hazard is somewhere in this block. So this signal can display a proceed at maximum authorized speed. And there's your simple 2-block system. A 3-block system becomes a little more complicated. The blocks are shorter than stopping distance now. We had stopping distance for a 2-block system. Well, now when we look at the chart here, we can see that this block is not stopping distance. Block B is no longer stopping distance between B and A. So what we have to do is actually look out. This signal says approach the next signal prepared to stop, but we haven't given them enough warning to actually get them stopped. So what we're going to do is add an additional aspect, and that's what I touched on previously. We're going to now include the aspect that has a flashing yellow, which upgrades the flashing yellow now upgrades the steady yellow on the approach. And that's telling you approach the next signal at medium speed. And what we've defined already is that this is at least medium speed stopping distance. So when the train arrives at C and gets the indication to approach the next signal at medium speed, at the next signal at B, he gets the signal to the indication to approach the next signal prepared to stop. He's got the time and distance to do that. And then on the outer signal, you can see on block D that it's displaying a clear because there's no hazard ahead. So there's your 3-block system, which adds just a little complexity. So now what we'll do is talk about some interlocking signals. We're going to add a diverging route to the design that we've already come up with. So we're going to have some more aspects. We're going to reuse the approach medium for a diverging, because we've already said approach at some reduced speed, so the rule book would define it. I'll discuss that a little more later on with some rules discussion. We need some new diverging aspects. So what we're going to do is add another head. So here you can see we've got an additional head here that's going to modify the upper head. So the top head will continue to be used for the normal route, and the bottom one will govern the diverging route. So we've now got 4 new aspects. We've got the so-called diverging stop. I made that up, by the way. It just simply means the same thing as a stop. Both heads are showing red or horizontal. That just means there's no route available. We have a diverging approach. The main route is not available, so it stays at stop, but the diverging route is now showing the approach the next signal prepared to stop. And I'll show you this in a track diagram in a minute. We have the diverging approach diverging, which basically says approach the next signal prepared to diverge. Just like we had the approach diverging, now we have the medium. So proceed through the crossovers or switches and approach the next signal prepared to diverge again. And then we have the diverging clear, which says the main route's not available, but the diverging route is clear, at least as far ahead as we can see. So those are the new aspects, the new aspect chart, and this is the full aspect chart except for the restricting that we need for the model railroad. And here's how we would do a diverging. So I've added another track here. I've called it A2 track, A2 block. A1 is the main block. A2 is the diverging block. We've got stopping distance from medium speed from B to A1. So our signal now with I said A1, but it's to either A1 or A2, but in particular A2. Our signal now at B is saying a diverging approach, which says approach the next, diverge through the crossover and approach the next signal prepared to stop. Our distance signal is C. It says approach the next signal at medium speed or diverging speed, because we have a diverging signal down there. And then, of course, out at D again, you can see we have a clear because there's no restrictions stopping distance ahead. These are stopping distance blocks. And for a clear, it would be very similar. You see the blocks are clear here. This is at least stopping distance away. There's no issue here. This is at least stopping distance. So we can display a clear on B, approaching the next signal. I go back to that 1 second. And you can see that the distance doesn't really change because it's saying approach diverging still, because you have to get through the crossover at diverging speed, and then you resume whatever authorized speed there is. All right. So let's talk about the restricting now. We already have the stop indication. We're just going to add an indication that look ahead, look out for the restriction, and we can do the same thing with the number plate or a flashing to upgrade that stop indication. If you look up above, you see the stop indication is just a steady red or a steady horizontal. And to upgrade it, all we have to do is flash it or add a number plate. And now we've got our full chart. And these are all the aspects that I contend that most model railroaders need to display something realistic. We don't really have to worry about diverging speeds and so forth. And even if we did, I can give you a workaround in a few minutes here. Now, we might want to have dwarf signals. You might not want to go to the trouble of having a mast with all those heads and all those lamps. So dwarf signals are typically either on the ground or on a very, very short mast. They're not intended to be visible from a distance. They usually don't have a background at all. It's just a light unit. And it's got a way different optical system than a high signal. These are a couple of examples. One is the one on the left is a straight color light. The one on the right is a searchlight. And the indications are usually only just for slow speed moves because you can't see them from far away. The B&O color position light doesn't distinguish that, and I'll show you that in a minute. High signals can also be configured for slow speed aspects. So think about what we just did with the diverging. We added a head to a high signal, have a two-headed signal. Well, we could add a third head, and that would govern only the slow speed route. I don't think model railroads need to go to that much trouble, but you certainly can. And Yeah, it adds a lot more lights. So I'm saying this is the basis of all signal systems. Different rule books call them different things. I made up some of the names here today. The railroads don't typically use some of the names that I made up, but the eastern roads today do favor speed signaling. So where I was interchanging the terms approach medium and approach diverging, well, the eastern roads would have, say, a approach medium or an approach limited or an approach slow. And uh, that would be associated with the various different routes. The western roads, and formerly the Erie Lackawanna, the CNO, and the NKP that were in the consortium there, used the diverging rule. So you would get a rule that would say diverging clear, approach diverging. And it was up to the crews to know the speeds at those locations. It made much simpler signal design, which is what I'm favoring here for a model railroad. But it put way more burden on the crew for knowing the actual restrictions at every given point and over every given switch. I did see it and it did work, but for a model railroad, I think it's overkill to go with the full-blown speed signaling. So let's talk about, maybe I should have done this before we actually started doing our chart, but let's talk about what the actual signals on the railroad look like. Here's a semaphore, typically a two-headed, this would be called a two-headed semaphore. And it's shown in the stop position there. Both arms are horizontal. You get the day indication just by seeing the position of the blades. And at night, there's usually a dim lamp. And if you look carefully, you can see the spectacle that moves with the arm in front of a lamp. And it gives you the different colors at night. It's not usually a good optical system, so it can't be seen from a great distance. And you can't do flashing aspects with the semaphore. And in reality, there's a lot of maintenance involved in them, so they're not real practical today. Position light. I know my friend John Swanson would love to be talking about these, but they can be a topic all in themselves. The semaphore is mimicked by the position of the signal lamps. In this case, we're looking at a Pensy style clear in the vertical semaphore position. The color position light that B&O uses both the position of the lights and colors and markers. And they can do some very complex signaling with very little head, but it looks complicated. And here's the dwarf I was talking about. On the B&O, that's considered, that dwarf can display the same signals as the high signals that are shown up here on the cantilever. And then you have the position color lights, which is what Amtrak is using today on the corridor, that adds color to the standard position light, the standard PRR position light, and it eliminates the neutral lamp. So in the case of the clear, what you would see would be two vertical green lights, the top and bottom green lights of the position light, and there would be no neutral, yellow neutral light. And then we have just a straight color light, and typically there's 2 or 3 light units in a vertical or triangular configuration on each head. We talked about the head. The head is it's a combination of the 3 colors. Here you can see all 3 of them. The top head is displaying a yellow. The middle head, believe it or not, that's a green. And the bottom head is a red. But all three heads are capable of displaying all three colors. This is the least complex of the various signal systems I've just talked about. And today it's probably the most cost effective. Each unit, each one of these light units, like the yellow, the green, and the red in this head, each light unit has its own optical system. There's an internal colored lens, and then there's a high power clear Fresnel lens on the outside, so that these can be seen from great distances. With these signals, only one lamp unit is lit in a head simultaneously. So that's why, although we're seeing all three colors here, this is an approach medium indication with the yellow over green, and the red is just a marker because it says there's no slow speed route available. And the heads are spaced appropriately so that you can see these way far away. These are typically 5 feet apart. In today's world, LEDs are replacing the colored lenses. And in fact, you can almost get rid of the entire optical system because the LEDs are so efficient in producing light and color, and they can't be washed out by sunshine like a conventional color light. They have much better color saturation. They have a long life, which means less maintenance or expense, and are very, very efficient. One of the places I forgot to mention with the color light, with the LEDs, is light out detection. For example, this signal here, if the yellow light were to burn out, it would be left from a distance. It would appear to be a green over red, and it could be interpreted by the train as a clear signal instead of an approach medium. With a conventional signal, there's detection available to determine that the light has burned out and prevent that from happening. With LEDs, it's very difficult to do that because it's typically an array of many LEDs, and you can't really detect when it's burned, quote unquote, burned out. One final version of a color light is the searchlight. These were used widely into the 1950s. Virtually every railroad had them. They have a mechanism mounted in here and behind the optical system that's similar to a vital signal relay that moves a colored disc in front of a single lamp. You can get by with a very, very small lamp and a very powerful optical system, but you only need one optical system, unlike a real color light. They could be directly controlled over line circuitry, and you could eliminate some relays that way, so there was some cost savings. However, two big disadvantages. Because it's a mechanism mounted up in the air and out in the open, it requires periodic and inspection and testing to determine that it's operating safely. And the other major downside is that the target is known as a target for very good reason, because in rural areas especially, it's very, very common to have it shot out. And that can potentially lead to a very, very hazardous condition if the mechanism gets jammed in the wrong position from broken glass or a bullet or whatever, and displaying the wrong color at the wrong time. So we developed now our aspect chart. I've added the color to this one. Since we've talked about the color and how it's interpreted, I've added the colored aspects to our chart, and this is now something that could be used by everyone on their railroad. So there's what I say is the full set of signal aspects that a modeler would need. Here's a real chart. This came from NJT. These are the aspects that the NJT train crews could possibly see in the course of their service. This has all the position lights, the color lights. There are no semaphores shown here because there's no semaphores left on NJT. Yes, thank you, NJT. I take credit for that. And it also has some of the B&O signals on there as well, which you could see in the Washington. Well, I guess it's only in the Washington terminal. So these are NORAC aspects, not really NJT aspects. And here's a full chart of the B&O style signals. Again, that's probably a topic in itself, similar to the Pensy. And so we're just about done here. So what I'm saying is by balancing the complexity of the system versus what we see, we only need the 8 aspects we developed today. If you want, you can use dwarf signals, or simply give a red for a stop and a yellow to go. And I think you get a realistic array of meaningful animation that you can add to your layout and still give the crews something about real operating information. I'm not going into the logic today. That's a topic that you could spend days on, but you can deduce most of it from what's available here. And based on some recent experience, JMRI has most of it built in. If you are familiar with building a panel with JMRI, most of the logic is already there and can be used to great effect for a model system. I know of several good examples in the area that have full-blown working signal systems. One is Bob Burke down in Appomattox. Bob Mashonis outside of Charlottesville has a subset of signals. Bob Rodriguez has a very good working system. And here's not a Bob, but Rick Lull is building a fabulous railroad down outside of Richmond that has a full-blown RF&P signal system. And that's it. That's my presentation. I hope it helps someone be able to do this. I am in the process of doing an install on my railroad now. I've acquired the hardware, and I'm in the process of doing the actual logic from JMRI, which is going to save me probably 10 years off my life. And hopefully within a year or so, I'll have a full-blown working signal system here. I'm open to any questions.
John, James Butler brought up a question about who determines what stopping distance is and whether it would be different for a passenger versus freight train.
Oh, it is. It's vastly different, and the railroads have their individual charts. It's not done by the FRA. although FRA typically is involved in the testing process for proving those charts. But each railroad has their own standards for the stopping, and it's by class of trains. Conrail had 1 million of them. Mineral trains were different from trail van trains, which were different from regular freight trains. And even Amtrak has, I hate to guess how many, but I can think of at least 8 different braking distance curves being used for Amtrak.
So I guess I'll ask the question now that since we know that there's a difference between the different types of trains, and you referred to the stopping distance as to in the signaling process, do we want to set the distance for the I guess most difficult train to stop, or an average, or what would we do?
If you want to make it look realistic, I would suggest that you go with the 3 aspect for freight. Well, go with the 3 aspect system because a freight train takes a lot longer stopping distance than a passenger train. However, in practical cases on the model railroad, it doesn't matter because unless you're a real fan of momentum and have a lot of momentum set in your locomotives, stopping distance is almost irrelevant on a model railroad.
Okay.
But if you want to play with it, yeah, absolutely. Go with the 3 block system and the 2 block system.
Okay. Does anybody else have any questions? Here's your opportunity to talk to our signaling expert today.
Good job, John. Thanks.